Now, the power you get from a solar cell will of course depend on the efficiency of the solar cell, whether it's 24% efficient or 28% efficient or whatever. But there are other, often bigger effects. One is you of course want to put your solar cell in a sunny location. So here's a graph we've seen before showing the amount of sunlight in Australia, taken from satellite data. And you can see that if you put your solar cell over here in outback Western Australia, you can get more than 6.5 kilowatt hours per square metre per day, whereas down in southwestern Tasmania, where it's further from the equator and cloudier, it's going to be less than 3.5. So that's about a factor of 2. You still get a decent amount of power down here, but clearly, other things being equal, you would put your solar cells in sunny locations. Once you've put one, even in a sunny location, the amount of power you're going to get will vary due to weather and during the day. This is a typical year's worth of solar power output from Alice Springs in the outback of Australia. So that's right about here. And you can see that it's generally higher in summer and lower in winter, purely because the day is shorter and the sun is lower in the sky. And you also get sunny days and cloudy days. So there's a big dip here. So in part of April this year, it looks like it was pretty cloudy for a while, whereas the winter was actually very sunny. So these are all factored in. Another issue is what time of day it produces its power. Now this is a rather clever set of graphs. What we have here is the day of the year across the bottom versus the hour of the day. And what we're looking at here is this is for Canberra, the ACT, Australian Capital Territory, and this is showing the amount of power that's used at different times of the day and the year. So what we can see is on the 1st of January, in the middle of summer, not much power is used between midnight and 6 or 7 a.m. and the power usage ramps up, and peak power is about in the evening, maybe about 6 p.m. and then fades off towards the evening. And you can see some of these yellow bands here. These are heat waves. Would be a week when it was very hot, and so what's happening is in the morning in Canberra it's not that hot, but then by about midday it's getting really hot and people are turning their air conditioners on. So the amount of electricity needed gets bigger and bigger. It's really at its hottest about sunset. And then as you go into the evening it starts to cool down, people turn off their air conditioning, maybe they're not watching so much TV or doing other things, and so the electricity demand goes away. So that's a typical summer pattern. If it's a cool summer day, not much electricity is used at any time. A hot summer's day, you're going to have air conditioning peaking around 5 or 6 in the afternoon. Then things change. This is autumn, then the power demand, not much in the middle of the night, then a bit of a rise in the morning when people are getting ready during the day, running their factories and their offices, and a peak in the evening when people are home or cooking tea. And then you get into winter. And in winter you're starting to see the effect of heating, because Canberra is cold in winter, and what you can see is that people are waking up about 7 in the morning and turning their heaters on, and there's a lot of electricity demand. The big bands here will be particularly cold days, or maybe the stripe here is for a weekend when people are at home all day heating all their houses. Then during the middle of the day, especially in the week, people are at work, they're not using their heating so much. And then everyone turns on their heating about 6 in the evening, and also cooking tea and heating up water for showers and baths, watching television, and so the electricity demand is there during the evening and then fades away into the middle of the night. So that, for a place like Canberra, is the typical demand pattern. Over here is what is actually produced by solar cells in the ACT. And what you can see is they mostly produce in the middle of the day. Got some daylight savings, pushes it back a bit here. And you get vertical bands, which are cloudy days, a few cloudy days in the winter there, but mostly it's a pretty sunny place, Canberra. I don't know which particular year this was for. The daylight lasts longer in summer and less in winter, and there's more intense sunlight. So this is a big factor because you can see that the electricity produced by the solar cells doesn't line up particularly well with when you need electricity. Most electricity is needed in cold places for the morning and evening peaks, and especially in winter, and that's not when the solar panels are producing very much. They are quite helpful for air conditioning in summer, but again they're not quite right because the sun is getting pretty low in the sky by 6 p.m. and that's when the peak air conditioner demand is. So that's an issue. Another issue is how you angle your solar cells. Here are typical roof solar cells, and these are normally, you're suggested to put them on a roof that's facing north in Australia and south in the northern hemisphere. But they're just fixed, they're pointing in one direction. Let's say it's pointing due north on a roof that's got an angle of about 30 degrees. That means that in summer the sun will be shining directly down on them and you'll get peak output. But as the sun sets in the west, the sunlight will be coming into a steeper angle, giving you less power per square metre. You can change this. You can have rotating solar cells that will tilt up and down and left and right, and so they can always track the sun. This gives them more power, especially early in the day and late in the day, and also in winter when the sun is low in the northern sky, they can tilt over and get more of it. So this definitely gives you more power and gives you more consistent power during the day. The drawback is it costs way more. You can't put one of these on your roof very easily. A compromise is the one angle tilting, which is used by many commercial plants, where you see all the solar cells are on a single axis and it pivots them so that when the sun's low in the sky they point over and when it's high they move back. And that's a lot cheaper to run than one of these two-axis systems and still gives you better power over more of the day than a fixed plant. So is it worth doing this? I mean, you could also do other clever things. Given you need most of the energy in the evening, maybe you could have lots of solar cells that face west, so they catch the setting sun. And there are certainly possibilities like that. The trouble is that at the moment, solar photovoltaic systems, the solar cells, are so cheap that the overall cost of a solar system, like this on your roof, is only about a quarter the actual solar cell. 8% for the silicon, 3% for the wafer processors, 6% for the cell processors, and 9% for the module processors. And the rest, what's called the balance of system, or BOS, 74%, is paying the person to put it on your roof, running the cables down to the ground, the interest rates you're paying to pay off the loan you got for it, and the inverter on your wall to convert it into alternating current. So the solar cells are actually the minimum part of it. Actually installing them costs more than buying the solar cell. So it makes no sense to have some very complicated installation like that. This was blowing the price out. You're often better off having something simple like this, or even just laying solar cells flat on the ground. It's not ideal for power, but solar cells are so cheap, the amount you save in terms of the workload of installing them more than makes up for the loss of power. So we're in a funny situation now. You can make these things better, but it may just not be worth it financially.